Okay, so in this problem 7.50 we have this circuit, and this is an analytical problem, so we're just going to find out equations, and we are assuming that the bias circuit that's not shown here, it's biasing the circuit to operate the BJT to operate in the active mode, so it works as an amplifier, right? And the problem it asks us to substitute the BJT here, okay, by its hybrid pi model without the output resistance, the small r out. Okay, so we're not including this one here, but we need to insert the r pi and the controlled current source, right? So in this circuit we have an input signal, a V signal here, which has a resistance R signal here. And in this problem we are required to calculate the input resistance, which is the ratio between V pi and IB. Okay, so it's this one here. We need to calculate the voltage transmission from source to amplifier, which is V pi over V signal. We need to calculate voltage gain, the voltage gain from base to collector, which is this one here, and the overall voltage gain, which is the voltage in respect to the ratio of V out over V signal. Okay, so in this case we are going to substitute the BJT by its small signal model. So we have a resistor here, we have a current source here, and this one here are the terminals. So we have here the collector, here the emitter, and here the base. So here we have base, collector, and emitter. This one here is R pi, and this is V pi. And this V pi you see in my drawing down there, that's also called VBE. And here's the transconductance times V pi or VBE. Okay, so we need to replace this. This is the hybrid pi model. We need to plug in here to substitute the transistor for that. So if we do that, then we get a circuit that looks like this. And again, this VBE here is also V pi. And for the input resistance, we just need to realize what's the ratio of V pi over IB. So if we represent V pi, which is the voltage across R pi, we know that V pi is equals to R pi times IB. Okay, and notice that I'm using small I, small b, because now it's a small signal analysis, so we just have this small signal component here. Okay, so if we isolate V pi over IB in this equation, we know that the input resistance of this amplifying circuit, the small signal, the input resistance seen here, right, is actually just R pi. So that's the first result that we got from this analysis. Now the second term that we need to define is the voltage transmission from source to amplifier. So it's V pi over V signal, and for that we can apply a voltage divider here. Okay, so remember this one here is, sorry, it's V pi, right? And we know that V pi, okay, if we apply a voltage divider here, right, is equals to the input signal voltage times R pi divided by R signal plus R pi. And again, if we isolate the ratio V pi over V signal, this gives us R pi over our signal plus R pi. And that's the voltage transmission from source to amplifier. Okay, our second result. For the third analysis, we need to define the voltage gain from base to collector, okay, which is the output voltage over the pi voltage. So again, this is V pi, and for that we can apply actually a loop analysis, but now here in the collector. Okay, so notice that I'm adopting the direction of the current counterclockwise, so it doesn't agree with the polarities of V out here, right? So we have, if we apply a loop analysis here, we have minus V out. That should be equals to Gm, and this one here is the same as V pi. So we have this current flowing through RC, that's Gm V pi times RC, right? Because this voltage source here, it forces the current through RC to be Gm VBE, or Gm V pi, the transconductance times V pi. Okay, so again, if we isolate the ratio between V out over V pi, we get minus transconductance Gm times RC, and this gives us the voltage gain from base to collector. Okay, our third term that we need to define here. So now that we have those terms here, so we can define the overall voltage gain. And the overall voltage gain, it's the same as the voltage transmission from source to amplifier, which is V pi over V signal, times the voltage gain from base to collector, which is V out over V pi. As you can see, V pi and V pi here cancels out, so we get actually the ratio V out over V signal. Now, if we plug in this equation here and this equation here from the previous calculations that we had, so this one here, which is R pi divided by R sig plus R pi, so it's R pi divided by R signal plus R pi times the voltage gain from base to collector, which is this one here. So minus transconductance, and it's times minus Gm RC. Now one thing is that we can rewrite V out V sig as minus transconductance R pi RC divided by R signal plus R pi. And one thing is that Gm times R pi is equals to beta. So the output here can be written as minus beta RC divided by R signal plus R pi. That's our last equation for this problem.